Okay, kids, we're going to start with gas homework number 1. We have to state the 4 variables that we can measure gases: pressure, volume, temperature, and the number of moles. These 4 variables are used to describe gases. Number 2, we have the kinetic molecular theory. Now, this is big, but I'll write some quick notes. Right, number 1, gases are made of hard spherical particles. I think I spelled that word wrong. This is not really true. Gases are made up of molecules that have a variety of different shapes, but they act like this. Because if they had shapes, they would bump into each other and get tangled up. Now, technically they do sometimes, but they get untangled as well. But this is talking about the perfect kind of a gas. Particle size is tiny compared to the space they take up. And this is true, right? All the air in this whole classroom would fit into my pocket if I squished it enough. So the particles themselves are fantastically small, and the space they take up is actually fantastically big. And an easy way to remember that is I run really fast in the air because the particles are far apart, and I run in between them. Okay, they have no attraction, and they have no repulsion. Repulsion, P-U-L-S-I-O-N. That's not really true either. All particles are slightly attracted or repelled from each other based on their relative charges. All right, the electrons are on the outside, they're moving around. Some molecules are bent and they have a slightly more positive or negative end. And of course, there's some attraction and some repulsion. But gases act like there's none of this. It's so small, it's not really that important. And, you know, the gases just bounce around and they stay gases. Another thing we can talk about, the particles move fast and in straight lines. This is absolutely true. Gases do not go loop-de-loop, they not hover, the particles are zooming around, and when they bump into each other, they bang off in very, very straight lines. It's almost like a big geometry test that's happening. The collisions are elastic. Now, what the heck does that word mean? My socks have elastic in them and it holds them up, and when I snap them, they snap back. Elastic collisions means when the particles collide, all of the energy is perfectly transferred to the other particles, so the average kinetic energy of a gas is constant. Now, in theory, it's really not true in real life. In theory, that's the truth, but there is, of course, a slight loss of energy due to the collisions, but it's so insignificant it makes no difference. The next part, let's see what else we can talk about. Average kinetic energy of a gas is proportional, AL, to Kelvin temperature. Hotter it is, the hotter a gas is, the more kinetic energy it has. The less kinetic energy it has, the colder it is. And we always use Kelvin temperature. Always have to have Kelvin temperature because we can't have a 0 or a negative number in the denominator. Number 7, collisions result in gas pressure. The more collisions, the higher the pressure. The stronger the collisions, the higher the pressure. Anything that increases collisions will increase the gas pressure, and anything that decreases or weakens collisions will decrease the gas pressure. Now we have to draw a graph now for number 3, a very small graph that has temperature in Kelvin, and then we have kinetic energy. And it says relationship between temperature in Kelvin as a function of kinetic energy, and it's directly proportional. Directly proportional means where one variable increases, the other increases. As temperature goes up, kinetic energy goes up, or they both go down. They both go in the same direction. Now, this line could also be drawn over here, or it could be drawn over here. The proportion does not have to be 1-to-1. Temperature could go up much faster than kinetic energy, or kinetic energy could go up much faster than temperature. When something's directly proportional, as long as both of the variables move in the same direction, not necessarily at the same rate, but in the same direction, that's going to be exactly directly proportional. All right, now, number 4, you may be fooled because you may think, oh, we're doing gases, we got to use the gas law formulas. We're not necessarily going to do that. Look at this. It says you have 16.2 liters of helium at STP. How many moles is that? Well, this is a moles problem. There are 22.4 liters in 1 mole, and the liters will cancel. And when I get my calculator in my hand, see if we can see these numbers, it's going to be 16.2 divided by 22.4, 0.73723 moles of helium. Number 5. How many grams of helium is that? Well, you have 0.723 moles of helium, and 1 mole of helium is 4 grams of helium. The moles will cancel. How did I know that? That's the atomic mass of helium, or the molar mass of helium. It's going to be 0.723 times 4, and it's going to be 2.89 grams of helium with 3 significant figures. This as unlimited, that has 3 significant figures. Question 6. How many atoms is that? Well, we'll start with moles again, because that's in the middle. And we know that 1 mole of anything, including helium, is 6.02 times 10 to the 23rd atoms, in this case helium. Moles will cancel, and it's going to be 0.723 times 6.02. So we'll write this number down, 4.35 times 10 to the 23rd atoms of helium. Number 7, it says, how is it possible to take 16.2 liters of helium gas and squeeze it into 1.0 liter container? How can you take 16.2 liters and squeeze it into 1 liter? And the reason is, if we drew a picture of the gas, the particles look like this. There's not a lot of them, and they're really far apart. And if we put it into a much smaller container, what do we got? 7 dots, 1, 2, 3, 4, 5, 6, 7. You want to put it into a smaller box? I'll put it into an even smaller box here. 1, 2, 3, 4, 5, 6, 7. Right? You just keep making it smaller, and so it's hard to draw, but you could even put it into a little tiny box like that. I just can't fit it. There's plenty of room because the atoms are so unbearably small. This is just a boo-boo here. All right? Now, it says, write the combined gas law. You should do this. It's on the back of your reference table. Now, the way we say that, P1 V1 over T1 equals P2 V2 over T2. P is pressure, V is volume, and T is temperature in Kelvin, exclamation point. Has to be Kelvin, has to be. And question, the last question there, I don't know what number we're on now. The numbers get all mixed up here. Why is it Kelvin? Why? We can't have zeros in the denominator, and we can't have any negative numbers in the denominator, right? We can't have negative number. Oh, I'm writing this down. You can't even see it. I apologize. This whole new age thing called Zoom. Why is it Kelvin? Because you can't have a zero in the denominator and you can't have any negative numbers in the denominators. Otherwise, the math falls apart. So we use Kelvin because I guess if it ever were 0 Kelvin, which it could never be, it would really mean 0. Otherwise, it's never 0. And it's never 0 because it can't be 0 in the math in a denominator. All right, that was homework number 1.